My name is Professor David Flynn, and I'm disappointed that I can't be with you all in person today, but it's my pleasure to raise awareness of our research and collaboration with Nagasaki University in the area of sustainable energy and robotics. So, the offshore environment is where our focus has been in the ORCA project. This is a very dynamic and complex environment where there is a lot of legacy infrastructure, as well as increasingly expanding offshore renewable infrastructure. At the same time, as we go through this unprecedented growth, we have an opportunity to capitalize on the unprecedented levels of connectivity we have through cyber physical networks. Now, the life cycle management of our critical energy infrastructure is key. And because we can now engage from generation, distribution to point of use, as you're seeing here, at global scales, like never before, we have some amazing tools and technologies at our disposal that can help us deliver sustainability and make human operations in these environments safer and more rewarding. The points of intervention that we focus on are predominantly in the operation and maintenance space. However, without a doubt, there are points for robotic and AI solutions at all points of the life cycle of these critical and remotely located infrastructure. So, something to think about when we use the term sustainability in the context of green technologies. So, the Global Wind Energy Council has actually forecasted that there will be 205 gigawatts of new offshore wind capacity by 2030. This is actually an increase on pre-COVID forecasts of over 15 gigawatts. Around 6.8 to nearly 7 gigawatts of that offshore energy will be from floating wind structures. Now, at the same time, we have this global political will, financial stimulus into this sector. We also have the tension to be managed, where we have the UN declaring a decade of ocean science to look at ocean resilience. So, in the quotations you can see here, just gives you an example, one initially from the UK perspective, of the level of investment and the prosperity associated with increasing renewable energy and the pathway to net zero. At the same time, we have to acknowledge that green doesn't always equate to sustainable, and our practices also have to be more symbiotic with the ecosystem and environment that we're engaging with. Because as we see evidenced here, around 40% of the world's oceans have suffered from harm as a result of human activity both on land and offshore. So, where could some of these challenges reside? Well, as identified independently with companies such as Ørsted, and Siemens Gamesa acknowledging this, 95% of all wind turbine blades are burnt or put into landfill at their end of life. So this is clearly an area for significant improvement. Could this be in original design? Could it be in circular economy? Either way, we can see there's opportunities for intervention and definitely a role for robotics and AI. As we significantly expand into the offshore environment for this offshore wind resource, this is going to result in about 16 billion of capital investment to deliver 2.5 million kilometers of subsea cable. So that will be processes that involve sea ploughing, concrete mattresses, rock dumping. So that is without doubt disruptive. If you were to speak to marine scientists, they would say, trawler net fishing has been devastating as a process to the marine ecosystem. So we have to be mindful of how we improve our collaboration with nature in that environment. Now, at the same time of this incredible motivation and investment into renewable energy, we also have similar levels of excitement around the potential of robotics and AI. Now, the UK government assessment of robotics and AI is that this is a high growth market. It's something that is already giving us significant returns, but there's clearly headroom, as it's defined, which basically means adoption rates can be improved if we can tackle issues around the barriers to adoption, the safety, the reliability, the productivity of these technologies. So today I want to give you an insight to some of the collaborative work we've been doing across the university partners of Heriot-Watt, University of Edinburgh, University of Liverpool, Imperial College London and Oxford, along with around 45 industrial partners and stakeholders through the Orca Hub. The Orca Hub is the world's largest robotics and AI research hub solely focused on offshore asset integrity. The vision of the hub is to support long-term offshore industry vision of a semi-autonomous energy field, operated, inspected and maintained from shore. So our mission is to drive this creative science and engineering into next generation products and solutions, and to support the UK supply chain in becoming one of the most productive in the world. So within Orca, we have 4 work packages or research themes, you could define them as. When we created these themes, it was after workshops with industry to understand the key capability statements they wanted us to achieve for their industry. So mapping, surveying and inspection, of course, having an accurate and computationally efficient picture of the world around us is clearly key to safe interaction and productive interaction with it. So this is just one example from our teams, and we are looking at land, sea and air robotics and looking to improve mapping systems, localization, very important when we consider the dynamics of the environment in terms of visibility, etc. And how do we build up these robust and accurate maps of the environment and space we're working in using different multimodal technologies. Another example, in this instance from planning, control and manipulation, our second work package, concerned with looking at the physical movements of robots in these high consequence and intrinsically complex environments, very cluttered spaces, not being designed with robot accessibility in mind. And in this instance here, what you're seeing is the adaptive planning and also the control required in order to both mitigate the risk and take an alternative route, and then to overcome obstacles encountered on that new pathway. Robot interaction with the environment is obviously incredibly important for inspection, but clearly also for manipulation tasks. This could be to add a stimulus to test a structure, or indeed to conduct a repair function. And as we can see here, Animal has then located the asset of interest now, and it can then conduct the inspection with the payload, in this instance, a thermal camera. Our third work package, this was looking to how do we couple and optimize human collaboration with multi-robot teams. So this was intelligent human-robot interaction with explainable AI. And what is playing in the background here is the Miriam platform, which can use text and speech in order to engage, query, in this instance, a fleet of 8 autonomous underwater vehicles. So what this gives us is that actionable information for the human in the loop, and the explainability of asking the team of AUVs as well as the individual systems critical requests such as, what is your state of health? Why is there a time delay on your arrival at the waypoint agreed? And it promotes this translation and engaging and coupling in a kind of symbiotic fashion between the remote human in the loop and the deployed field robotic systems. And obviously this would need to be tailored for a range of end users, which could be from technicians, asset directors, etc. Because how we engage, as in the symbolism, the priorities that we apply, will vary for the individuals. Our fourth work package was focused on robot and asset certification. So to explain what that means, the laptops that you're using just now, your mobile phones, they all have certification that say they're legal to be used. And that legal definition has been based on safety and quality compliance. Now, given that robots can have different levels of autonomy, so devolved responsibility, interacting with people, other robotic systems, infrastructure, and the environment, we felt a new standard was required. And we called this standard self-certification. How could we get runtime diagnostics and prognostics that reaffirmed that the robotic platform was still in a safe state of health in order to fulfill its mission? So we developed concepts such as reliability ontologies, edge prognostics, in order to give us a proper understanding, a more informed understanding on the state of health and remaining useful life of these field robotic systems. Now, we took the principles of that process, that methodology, and we also applied it to subsea power cables, because we had discovered, by looking at 15 plus years of historical logs from one of the UK's largest subsea cable asset owners, that 70% of the failure modes of these cables were not being monitored. And these failure modes were associated with ambient factors. They were basically abrasion, corrosion, and third-party impact. And those mechanisms of failure were not being detected by the current state of the art of online, partial discharge monitoring, which is predominantly looking at electrical condition monitoring. And given the amount of legacy cables we have out there, The likes of fiber optic technologies was obviously not an option. So what we had created was a low frequency wideband sonar, taking inspiration from the likes of dolphin sonar. So this would give us an integrity image of the subsea cable structure. Now, to create a really informed and verifiable model, we took sources of data and information from multiple sources, and we created what we call fusion prognostics. So we took historical offline data, we took in situ seabed topography information, we took cable manufacturer information. We were then coupling this with some experimental life cycle testing data to understand how these structures may degrade for different cable types over time. And we were then able to integrate this to give us, you've seen briefly, an acoustics and color kind of image. The end result of this work was that we were able to forecast the failure of cables within plus or minus 1 to 2 months of their lifespan. And their lifespan, for some installations were about 50 years. For the other installations, you could be looking as short as 2 to 3 in highly dynamic environments. But more typically, you're looking at, 15 to 20 years. Now, that level of accuracy was actually excellent because to operate offshore, you need to mobilize your logistics and your materials about a year in advance in order to kind of, reduce your operation and maintenance costs. Okay, so I want to move on now to looking at, so what does the future look like? We've done a lot of short mission case study work in this area, and building on that point I was expressing to you about cyber physical systems, I believe we now have a lot of the enabling technologies to look at more sustainable operations in order to improve life cycle asset management in the offshore space. And before I give you an insight to our most recent work, I felt it was really interesting to highlight this slide on managing expectations and delivering value when we think of autonomy and autonomy as a service. So Toyota, fantastic company, great resources, great technology. There was an incident at the Paralympics. It transpired it was human error, but it did cause a disruption to the use of the e-pallet system. If we then take an example of Amazon are struggling to deliver through years and years of investment into their drone delivery system. Again, great company, fantastic resources, great technology, but they're struggling to deliver this service. Also, Tesla, a household name, their successes and failures in their automotive autonomy is well documented in the media, with a range of factors associated with it, from intrinsic system failures to human failures in terms of misunderstanding of the responsibilities or neglect of responsibilities. So it presents a really interesting question, managing expectations. So if you look at some of these figures here in terms of, automotive autonomy, you can see that based on this data, which does come from Tesla, we are seeing that mileage per accident with the autonomous assistant is incredibly improved. The US government independent automotive authority, the NHTSA, is highlighting that there is a likelihood that if you drive for 36 years, you will on average be involved in at least one accident. So this is a really interesting tension here. Okay. In other aspects of life, say for example medicine and even vaccines, there are acceptable risks. We know autonomy as a service, we're still dealing with that tension of how safe is safe enough. Arguably, we could be making positive interventions now, but in the acknowledgement that the system is not flawless or perfect. So that's an interesting tension. An observation is when I look at these three brilliant companies and their impressive technologies, I would argue that they've had too much of a product-centric view, which has its place. Design for reliability, design for manufacture has significantly advanced our capabilities in designing and manufacturing brilliant technologies. But the failing is in the service, and the service operates in a dynamic environment, interacting with different people in different locations in different ways. So I believe there does need to be more system of system thinking if we are to deliver resilient, reliable and safe autonomy as a service. So this has driven my group's thinking on a symbiotic system of systems approach. How can we create collaboration, cooperation and corroboration across the environment, the autonomous assistance, the human in the loop and the infrastructure? So to achieve that, we need a cyber physical network that allows the leveraging of the benefits and the attributes of each of these systems to kind of co-inform and advance each other. So a kind of schematic of what this looks like moving forward. We have created what is called a symbiotic digital ecosystem. We can currently in our labs incorporate around 1,000 different devices and autonomous platforms into one digital commons and coordinate them with a human in the loop. Looking into the future on the right hand side, where I've labeled it Adapt and Thrive, I believe this increased connectivity will allow us to not only be robust to disruption, but actually explore adapt and thrive opportunities. For example, if we see within the supply chains constraints on composite material availability, we know to then instigate an appropriate response in asset life extension in order to mitigate some of the risks that may create. So today, to prove some of our principles of this, we have run some experiments in constrained environments, and the deployed technologies look like this. If you look to the left-hand side, this is the human in the loop side of the equation. We have this digital commons where we have synchronized distributed technologies and their digital models into the same space with full bidirectional communication and distributed control. Above that grey interface is what we call the meta-twin, and that allows us to explore scenarios and capabilities prior to then pushing through into the resident cyber-physical system, the physical actions and requests that we have. I will now show you a wee video of one of those experiments that we've been running. So in this experiment here, we have a resident Husky system instrumented with radar technology for doing asset inspection, and also it has the arms that you can see on it in order to do manipulation tasks. This mission was in an industrial facility, which was a constrained environment where humans are not permitted when certain systems are in operation. Now, whilst the robot goes through different stages of its mission, it engages different subsystems. And this is where our reliability ontology comes into play. So you're about to see a daisy chain type graphic emerge. And what this is doing is mapping the interdependencies and relationships across the subsystems within the robot. Okay, and this is what helps to inform our in situ self-certification and understanding of the system's reliability. The data, which is very unique in this instance, it's a new radar technology we've patented called FMCW, is fed back to the end user to then incorporate this into other offline information. We have a fully synchronized real-time digital twin of the resident system to allow us to query, challenge and verify some of the information that's coming back to us. So, in the future and in our ongoing research, which will end at the end of March, we are creating a physical representation of the offshore environment in our labs and using the lab environment to create a dynamic space so that we can change the safety case. We can create obstacles. We can explore the resilience of a cyber-physical network of a multi-robot fleet working with a human in the loop. And the reason that we're doing this is that the barriers that we see to adoption relate to resilience, safety compliance, and reliability. So one of the biggest enablers for autonomy as a service is having a cyber-physical architecture that allows us to tune to the application with different multi-robot systems and allow us to address those key barriers in a timely fashion. Some closing points here in terms of sustainable energy and robots. We need to carefully manage the tension of offshore infrastructure and lifecycle management in the environment. We cannot just use green technologies, we have to actually reconsider our practices and the legacy implication of these practices. Systems thinking within a real-world context is vital. A lot of research in robotics is using customized off-the-shelf technology. This has been good for early sprints and quick learning. However, sustainable solutions require more systems thinking, capturing the real-world complexities. I do foresee a future for my team's symbiotic system of systems approach as a means to unlocking human potential with scalable autonomous assistance. And finally, looking at the global scale and the fact that we are looking to a global response in regards to climate change, I can see networks of cyber-physical cooperatives being integral to how we put the world onto a pathway of sustainability and prosperity with respect to our vital energy services. So I'd like to thank you all for your time. I would also like to thank my colleagues for their excellent research and support as well as that of our partners and sponsors. Of course, please feel free to access the publications which are accessible through the links provided, and of course I would be very happy to engage with any queries that you may have via email and conference calls. I wish you all a very successful event, and I look to see you all in the near future. Thank you.